Welcome back to the Multi-Hazard Engineering Collaboratory on Hybrid Simulation video tutorials. This time we will talk about PID control. First, it is important to refresh our knowledge of closed control loop systems. In a typical control loop, we have a system in which we provide an input and want to obtain an output response, such as a displacement, velocity, or acceleration. We have learned that actuators help us enforce the desired input value on our physical plant, and that sensors, often part of the hydraulic actuator system, measure the output and provide feedback to the overall system. Now, our input is what we want to see, and our output is what we're actually seeing. The difference between our input and feedback, or measure response, is called an error. To compensate for this difference, we need to use a control system algorithm, such as a controller, that determines the needed output enforced by the actuator to decrease this error. The PID controller is the most used compensator or algorithm in control systems. PID is the acronym of the three mathematical terms of the algorithm: proportional, integral, and derivative. The proportional term depends on the difference between the input and output. Its gain determines the ratio of output response to the error signal. So the proportional output is the product of the gain and measurement error. Let's look at an example where we have a simple mass spring damper system with the following characteristics and the governing transfer function. We set our input to be a unit step function, and for simplicity, we have taken the actuator out of the system. Compared to the system with no controller, the proportional gain helps the system reach an amplitude that is close to what the input is, decreasing the steady-state error. At the same time, the proportional gains decrease the rise time of the system, providing a quicker response. But the downside of the proportional term by itself is that higher gains cause overshoot and lead to oscillation, which can lead to further problems. Now, if we move to the integral component and make it part of the controller, it is able to sum the error over time and helps drive the steady-state response to zero, eliminating the offset. The efforts to control the steady-state response are mostly done by this factor. If we go to our system example and compare it to no controller and proportional only responses, we can see that increasing the integral correction factor reduces the steady-state error significantly. An integral factor may also decrease the rise time. However, such as the proportional gain, as the integral factor increases, so does the overshoot and settling time. We introduced the derivative component, which helps control the rate of change of the error. The derivative aims to counteract the rapid changes caused by the proportional and integral factors. It aims to anticipate the future behavior of the plant through differentiation. In our mass spring damper example, we can see that as we increase the derivative gained, the overshoot caused by the proportional and integral factors is decreased. We also observe some beneficial changes in the rise time and how it decreases the settling time. However, in more complicated systems, one must be careful with the derivative component because it can make the system highly sensitive to feedback noise. Adjusting the control parameters is known as tuning, and there are multiple techniques to do it. Frankly, there is no single answer or best parameters, but tuning of the PID gains depends on the needs of the user. The gains of the PID controller can be obtained through trial and error by subjecting the system to a step response or a simple input, or they can be determined based on specific performance requirements such as overshoot, rise time, and settle time. Parameters can also be tuned offline and online through sensitivity analysis. Another option is to use available tools to automatically choose optimal PID gains. These are available in MATLAB and LabVIEW, among other software. PID controllers and variations of it are quite popular in hybrid simulation because of their robust performance, wide range of operating conditions, and their ability to provide stable and improved system responses. They serve at the interface of the numerical and experimental substructures, controlling the hydraulic system so that the hybrid simulation can be implemented successfully. And often, people tend to trade off one characteristic of a control system for another to better meet their requirements. Thank you for watching, and continue to visit our YouTube channel for updates.